joining. So this talk today is called Needles and Haystacks, and it's really about how you can identify those needles in the haystacks that are the data that we work with in the data science landscape. Obviously, imbalanced learning is a really common problem in so many different areas of data science. So I thought that this talk would hopefully be quite broadly applicable to anyone that is kind of getting started or is already working within the data science or machine learning community. So as mentioned, yeah, I've had plenty of experience and time working in the sort of data and advanced analytics fields, delivered numerous projects in the sort of data and AI space, and I've really sort of gleaned from that quite a bit of experience about handling imbalanced data sets and kind of the problems that goes with that, and have kind of got a few different tactics and approaches that we can use today to help solve that problem. So what we're going to look at today. So first we'll talk about what is class imbalance. It sounds pretty simple to understand, but I think it's good to just really outline what that means, and more importantly, how do we identify it in our data so that we know that we're either working with an imbalance problem or we're not. Then we'll look at some of the more simplistic approaches. So these are the kind of things that generally you would try first, and are maybe slightly quicker or sort of simpler to implement. And then we'll have a look at some of the other approaches that exist out there, and these include, you know, training algorithms in specific ways or using some slightly more advanced techniques to try and balance out your data. Lastly, we'll have a look at a summary, and we'll kind of have time for Q&A at the end as well. Throughout all of this, I've got a few demos that I'm praying are going to go well. So we'll talk through a few of the code items that we can kind of look at that help us to identify or rectify imbalanced learning problems. So without any further ado, so what is class imbalance? So it's often also known as data imbalance or target distribution imbalance, or I'm sure there's a million and one other names. Essentially, it's a name that we give data sets when there is one class is more overly represented than another. So in this case, we have a severe class imbalance where we have one very strong majority class, and then we have that minority class, which has much less examples belonging to it. And as you can see, there are often times when you have a severe class imbalance, but there may also be times when you have just a slight class imbalance, when actually the majority and the minority classes are not too dissimilar. Also, you know, some people, if you're more sort of SQL literate, you know, you can identify these things and see them as in a sort of a tabular representation here, where you can quite easily see that class number one, so our positive class, has much fewer examples than our negative class there. And you can see the SQL script on the left there, which we'll talk through in a little bit, can help you identify that class imbalance. So the reason why that an imbalanced data set is such a problem and needs to be resolved is because of what we call the accuracy paradox. And this is where a model simply learns the underlying sort of poor distribution of that target class and simply says, I can represent that in the model, and that should give me a fairly good accuracy because of the fact that the target class is so minimally represented. So to make this a bit more clear, we can kind of visualize this. So if we've got a data set here that says a 10% sort of minority class versus a 90% majority. So we've got a severe class imbalance here. There's lots of minority examples that we don't have here to match the majority. When we feed this into a model, the model can actually see, okay, well, we've only got 10% here in the minority class. So almost if I just say, well, everything belongs to the majority class, everything's going to be a negative, I'm going to get 90% accuracy. So, you know, which in most kind of scenarios, in most worlds, that would seem quite good, right? 90% accuracy, that's certainly not to be sniffed at. But the problem is here, but every prediction that the model is making is going to be negative. It's going to be zero, just so it fits in with that majority class and therefore gets that 90% accuracy. So that's why we have to be really careful that we're not letting this accuracy paradox kind of skew our view of how well our model is doing. And it's really important that we look at some of the other metrics or look at ways to tackle that class imbalance to make sure we're not falling foul of the accuracy paradox. There's obviously many different causes of class imbalance. Generally, they fall into kind of three broad categories, although I'm sure there are others out there as well. The first is sort of bias sampling, and this is quite often the case. So, for example, if we're looking at a data set and we're looking to kind of build a model that might solve a problem for, say, age ranges between 0 to 60, if we only take sample data from some of those kind of age ranges and not the full set, we may find that we have a very sort of reduced set of target classes that we're looking for. We may well get this problem of class imbalance. Whereas if actually we'd sampled the entire set, we've been more thorough with our data sampling, we may then actually realize that actually we haven't got an imbalanced learning problem, and actually our target classes meet what we need them to be to get accurate predictions. So making sure that our sampling is accurate and thorough is really, really important. The second is kind of measurement or human error. And these things can be really, really common and often very, very difficult to identify because, you know, it's kind of that kind of common concept of the unknown unknowns. You don't know what you haven't done correctly. A really kind of good example of this is to share is the classic XLSX to XLS problem. And it actually was one that was in the news not so long ago throughout COVID. But if you take a standard XLSX file, standard Excel file in the modern day, that has a maximum capacity of around just over 1 million rows. If at any point that spreadsheet finds itself turned into a .xls, so without the extra X, you suddenly are chopping off the bottom half of that data set and reducing your max row count to 65,000 rows. So that's a whole lot of data that's just going to disappear. And if that's got, you know, a majority of your minority class labels in, for example, you're going to lose those. So that's kind of, it's, you know, that's a bit of an example there, but there are many other ways that measurement or human error could be introduced and would therefore, you know, give you an imbalanced learning problem. And of course, it may just be part of the problem domain. So there are several examples, for example, customer churn and spam detection, where what we're looking for simply is, you know, it simply is the minority. It's a rare occurring event. And that actually, if that was the other way around, then the problem wouldn't exist in the first place. So classic example there is customer churn. You know, hopefully more than not, your customers will stay with you or they'll purchase that particular product. On the rare occasion where a customer does leave, then that's the behavior you want to try and isolate and identify. But obviously, if that was the majority of behavior, then there'd be a whole different problem at hand anyway. So sometimes it is just part of what we're trying to do. It's naturally an imbalance problem. And other things that kind of sit within that, some other common examples of class imbalance. So spam detection, customer churn are the two that I've just kind of spoken about there for a moment. Obviously, fraud detection. So, you know, most of the time that a transaction will be a genuine transaction, whether there are some very rare occurrences where that might be a fraudulent transaction. So being able to identify that fraudulent transaction is very, very important. Obviously, anomaly detection is critical, particularly in sort of like manufacturing industries. So, you know, looking at what's going on in a factory and understanding if a particular temperature is flagging anomalously or a pressure gauge is flagging anomalously. Being able to identify that is really important, but obviously those events are more rare than they are frequent. So being able to kind of understand that data imbalance is really key. And lastly, things like claim prediction or outlier prediction, again, all these kind of very similar to anomaly detection, but they're about trying to identify that rare event that is going to make a difference to your business. Okay, so let's take a little look at a demo and see if we can sort of look at how we might identify some of these class imbalances. So I've got a little demo here set up. I'm using Databricks notebooks, but these are very similar to Jupyter notebooks if you haven't used Databricks before. Essentially, I've just got some Python code that is running in a notebook environment here that I can use to sort of demonstrate how we can check for class imbalance. So all I've done here is I've read in a data set, and actually this particular data set looks at diabetes in pregnant women. And it's just quite a well-known imbalanced data set that is also quite simple to understand. There's not too many features. So it's quite good for this sort of demoing of this kind of problem. So I've read this data in and I've got this data available to me here. And we can see I've got my target flag of positive for diabetes here on the right-hand side. So that's very simple. We've got our data. So the first we want to know is there a data or a class imbalance inherent within my data set? And actually, this could be shortened to one line of code, really. In 3 lines of code, I can very easily tell that. So if I run my query here, you can see that by doing a simple group by and count, I can see that, yes, there is a class distribution problem here. We've got 500 examples of negative for diabetes and only 268 examples of positive for diabetes. So you can see there we have definitely got a class imbalance against the majority class, which is negative, and the minority class, which is positive. So that was kind of using a Python or a PySpark version. We can also do exactly the same thing in SQL. If I register this as a view, I can run a SQL query. So those that are more familiar with SQL, obviously these things exist as well. So depending on where your data is, you can, if it's in a lake or in a database, you've got SQL options, but you can see we get exactly the same output here. That's all well and good. Sometimes we have to sort of present these things to people though, and have to try and make it clear to people that might not be so clear on what a data imbalance means and why that's a problem. We might have to kind of explain it to them and show it to them. So we can also visualize these things. And these visualizations are very easy to set up, particularly in Jupyter notebooks like this. We can generally click new visualization and that gives us all the options we need. Or of course, you could, turn this into a matplotlib type chart and export that out as well. But using those visualizations is really useful. Also, in some cases, there are profiling tools around. So Databricks actually has a very good data profiling tool built into it, which I can refresh here. But there are many other libraries and imports and this kind of stuff that you can bring in to give you a really detailed data profile. And these can actually be really useful, not just for identifying an imbalance on your target data, but also across a number of different features and showing you things like how many of those columns are empty, or what percentage are nulls, what are the unique values, what's the average length of that column, for example, what are the distributions. But importantly for this topic, we can see, yeah, okay, this profiling tool has shown me very quickly, I've got a data imbalance between my negative class and my positive class here, besides all the other detail around it as well. So that's really a useful way of looking at that. And the last thing to consider is that a data imbalance or a class imbalance may manifest itself differently through different slices of your data. For example, if I use this SQL query to have a look at only records where the age of the kind of the example, the woman in the record is less than 40, you see we have quite an extreme imbalance. So 70% belongs into the majority class, the negative, whereas 30% are in the minority class there, which are positive. That's quite a severe class imbalance. If I then look at the slice of my data that is over 40, the problem itself changes entirely. We're now almost at a 50-50 split between positive and negative for diabetes in pregnancy. So it's good to be aware that if there are other cases where you might have to filter or slightly differently slice your data or resample your data in any way, that class imbalance may also change in that different slice. So just being aware that it's not always a permanent and sort of static thing is an important sort of recognition, I think, when looking at data imbalance. So that's the end of the first demo. So I'll jump back to the slides. So the next thing we're going to look at is, okay, we've identified class imbalance. We know there might be some sort of, some issues there. We need to go and rectify that. We need a solution to help us tackle that so that we don't fall foul of the accuracy paradox. So now we're going to look at some of the simple approaches that we've got available to us. The first is data collection, extended data collection. And this one I've kind of included for completeness, although I do actually have a bit of a problem with this in that most data science teams probably exhaust all methods of getting data into their, getting their hands on as much data as possible before they start tackling too much the actual data science itself. So kind of to say flippantly, just go and get more data, I think is a little bit backwards to most data science teams who've probably already gone through that quite exhausting and quite extensive phase of a project. So, I think the other thing to think about is, well, are there slightly more dimensions to the data that you can look at? Potentially is, maybe you've exhausted all options inside your organization. Are there things outside of your organization that might be useful? External systems or other providers, maybe even some commercial arrangements where you're able to purchase data sets that might be of use. So just trying to think outside the box a little bit is probably some good advice. But generally speaking, most data science teams, I think, will have exhausted all options for data collection before they start doing any data science. The other thing actually is to look at different types of sources. So if your team is very used to working with databases and flat files, but hasn't maybe experimented looking into APIs or maybe other open sort of data sources, then potentially that's another way of saying, well, if we bring in a capability to actually read from that API or pull that sort of open data source down from the internet or something, then that could potentially open up more options to have data brought into your environment and into your data estate. The one thing you have to be aware of is that if you are pulling from external data sources, of who is maintaining that data, how reliable is it going to be refreshed as much as I need it to be? There are all those kind of other considerations, but hopefully expanding your box a little bit about where you can get your data from can certainly help. And the other thing to just mention here as well is that occasionally a data point that might seem useful can actually be achieved via a proxy. So a good kind of example of this is if you wanted to look at air quality data, for example, for a particular region, one option would be, of course, to kind of put sensors all around it and pull data off of those sensors. But that'd be very expensive, very difficult to do. Chances are you probably wouldn't be able to get that kind of signed off by the board in too great a hurry. But potentially if you could look at traffic data from an open data source on a government website for that particular area, that would give you a pretty good indication, a pretty good proxy of what the air quality data might be for that particular area. So sometimes just being a little bit creative, thinking outside the box can actually let you extend your data collection in maybe ways that weren't previously considered. The other options include sort of resampling existing data. So this is kind of a bit of a blunt approach. We'll talk about a slightly more kind of sophisticated approach in a bit, but this is more of just trying to, can we just rebalance that data? If we just shift some data around, can we actually balance it out a bit better? So one of the first options here is kind of oversampling. And this one is probably the most natural, obvious kind of solution to this kind of problem, right? Can we just replicate, duplicate, or copy our minority classes to meet the number of majority class examples that we've got in our data set? So oversampling, or oversampling with replacement, as it's sometimes known, just means copying our data over and over again until we've got the same number of minority class examples as we did for the majority class. And that's all well and good, but we're not generating any new data here, okay? We're just copying the same examples. So we're not giving the model anything new to learn on. We're just giving it more of the same, basically. So there's some downsides to that. The other one is obviously the opposite of that, right? We can take some data away from a majority class so that it then meets our minority class in the middle. And again, this seems kind of okay. We sort of, at least we're kind of balancing the problem, but also we are taking away a lot of data from a majority class, which is essentially depriving the model of things that it could learn. So again, not an ideal solution. There's also the concept of over-under sampling. This is where we actually combine both of those things into one solution. So our minority class, we may add some examples to through replication. And the majority class, we may take some data away, but hopefully we're able to find a sort of a good middle ground where we're not adding too much of the same, and we're not also taking away too much key information, but we're still able to kind of balance those two classes out. So that's that over-under sampling. Generally speaking, though, when you have sort of less data, so like less than 10,000 records or whatever that sort of threshold is around there, then oversampling is going to be the right thing to do, because you want to, improve your data. You want to have more data than that. So generally speaking, less data, you're probably going to look at oversampling. If you've got lots and lots and lots of data, if your data is in abundance, then potentially you could look at undersampling instead of oversampling if you feel you're able to kind of take that data away from your majority class. The other thing to consider with resampling is stratified sampling. And stratified sampling can be very, very useful if you want to miniaturize the problem. If you've got a very, very large data set that has an imbalance within it, and you want to try a number of different solutions to kind of solving that imbalance, you might want to make that problem a lot smaller, reduce the number of rows in your data set, try a number of different fixes quite iteratively and quite quickly. And then once you found one that works, then you kind of upscale that back to meet your original size data set. And in this kind of little toy example here, we've got triangles, circles, and squares. A non-stratified sample, for example, might give you just all triangles, for example. It might just give you randomly picked records from the set, and actually that might not be so useful. A stratified sample will ensure that when you pull your data out, it gives you a reduced set, but it mimics the same distribution of that data that you're looking to represent. So it can be very useful when we're trying to kind of make a problem a little bit smaller whilst we're testing before we then upscale again. Another one that sort of is a bit of an honorable mention is this process called active learning. And active learning is more when we take a data set, a large data set, for example, where we've got some target labels, but we're missing some labels for a large portion of those records. So on the face of it, it may appear to be almost like an imbalanced learning problem because we don't have so many of the labels that we're looking to use to teach our model. But what we want to do is we want to then apply labels to those so that we can actually identify if this is an imbalanced learning problem or not. So this is called a human in the loop type of learning, because we're going to use the model, which we're going to refer to as our learner, to sort of learn the process, but then identify which records or which examples it actually struggles to classify either way. And these ones we're then going to hand to a teacher or a human who's going to label them. And then our model can then learn the difference between those two classes more helpfully by identifying the records that it struggles to learn. So in this case, we would essentially split our data set in two, and the first one where the label's attached, we would pass that over into model training. And the second set where we don't have labels, we would pass that into a scoring algorithm using that model, and we would get the output of that, which would then have a prediction on it. So in this case, we predicted maybe 2 plus signs in a square, just to keep things really, really simple. We would then take that prediction, and we would also put alongside it the confidence score that's associated to each of those labels. And we can see here that the two lowest confidence predictions, those two plus symbols there, we would then pass that over to an expert who would then correctly label those examples for us. So in this case, the expert has said, right, actually that first one should be a square, but the second one they've actually got correctly, which is a plus sign. This would then feed back into the training process, and then we can iteratively train and then examine our kind of a model over and over again until we have an accepted level of labels in the data set. And then obviously we can identify, are we looking at an imbalanced learning problem or not, because we've got enough of those labels. The other thing that's really important to look at with imbalanced data is the performance metrics. And this is, again, because we're aware of the accuracy paradox now, which is going to say that a model that just predicts everything as in the majority class has a good chance of having a fairly high level of accuracy, depending on what the distribution of data is, depending on the relationship between your minority and majority class. And the thing that this all starts with is called the confusion matrix. And those that have sort of done any kind of data science and machine learning will probably be intimately familiar with the confusion matrix already, as it's kind of the cornerstone that we use for a lot of our kind of model evaluation metrics. What we're looking at here is a kind of a grid that tells us the different types of errors that our model is making. So in the top left, we've got the true positives. In the bottom right, we've got our true negatives. Bottom left, we've got our false positives. And in the top right, we've got our false negatives there. So these kind of the green sort of section there, that's our kind of our correct predictions. These are things that we're looking to kind of get high numbers from. So these are the ones we've correctly predicted a positive or a negative class. And these are errors. So these are ones where we're showing as not predicting something correctly. And the thing to really kind of call out here, so a false negative error, so that kind of 6 in the top right-hand corner, this really identifies the people that are, or the records that are slipping the net, in a sense, that if we want to make sure that we're really identifying those key classes, this is the number we want to reduce. A good example here is, diabetes in pregnant women. Obviously, we want to make sure that no one accidentally gets, classified as not having diabetes when actually they would do. It's really important that they don't slip the net in that sense. So reducing those false negatives is really, really important. The other side of that is the false positive errors. And these highlight records that are going to dilute the kind of the quality of your prediction. And these can be quite important too, because if a false positive indicates that, we're going to say, for example, in an anomaly detection, say we've got a pipeline all the way over the other side of the world, and a false positive comes up to say that pipeline has got a leak. We dispatch a 10-person team all the way over to the other side of the world to go and investigate it. Turns out it was a false positive. That's a very, very expensive reaction to a false positive. So if we have a very, very expensive reaction to a positive prediction, we want to really, really make sure we're minimizing the number of false positives that come through. So depending on sort of the outcomes of those two areas, we can look at whether we want to maximize our false negatives or minimize our false negatives or minimize our false positives. That's our confusion matrix. The next thing to look at is some of the other metrics that actually then fall off of the back of the confusion matrix. These are things that we use the confusion matrix to then help us calculate. And the first two of these is really the precision and recall. So precision is looking at, of the positive predictions, so the kind of examples that we predicted to be positive, how many of those were actually correct? How many of those were actually correctly predicted? And that's really, really useful for us in a number of different ways. The other metric to the side of that is then the recall, which is kind of almost the opposite, which says of the positive samples, so the examples that we were given that were positive, how many of those did we correctly identify? And that will then really help us know how many of those individual records are we letting slip the net, for example. So these two precision and recall metrics are really what we're trying to balance in that trade-off between false positives and false negatives. And we use precision and recall to help us understand those. The last one I was going to talk about on here is the F score. And commonly this is known as the F1 score, which essentially is the harmonic mean between precision and recall. It's kind of finding that best balance between precision and recall in that trade-off between precision and recall. So F1 basically means to find the perfect balance between those two. However, we can actually use the beta parameter to say, focus on one metric over the other. So a beta parameter that goes more towards 2, so is above 1, essentially leans more towards recall, whereas if we start to dip that down towards 0, then we start to focus more on precision. So the F1 score is where beta is 1, but we can actually vary that if we want to emphasize recall or precision, depending on whether we want to reduce the false positives if it's going to be a very expensive outcome of a positive prediction, or reduce the false negatives if the risk of someone slipping the net is actually very, 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 very bad, for example. Okay, so let's jump into another demo and have a look at how some of those different approaches actually get applied in our code over here. I'm just going to bring this across. So again, I've loaded my data set in and I've got my data available here. I've also done a few imports as well to bring various different classes that I need to use for this particular demo. So the first thing that we talked about was this oversampling. And this, again, is a very sort of simple, quite a blunt approach, but can be quite effective. It's very, very quick and easy to implement. So in this first cell here, what I'm doing is I'm essentially defining my two strategies. And I've used two just to kind of show the different approaches that we can use. The first one here is called the minority strategy. And all this does is simply say, boost the minority records to meet the number of majority records. But I can take a slight variant on that. I can also say, well, actually just make the minority class up to 80% of the majority class. So again, if I was looking at maybe doing over under and want to meet those in the middle, I can use those different strategies to help me do that. So I'll define my two strategies like that. This first one then is going to then use the minority strategy here. So as you can see, before resampling, we've got our 500 examples here and our 268 of the positive class. After my resampling, now both have got 500. But it's just simply copied the data up until I've got the same number of examples on both sides of that equation, if you like. So again, a very sort of blunt brute force approach, but has clearly balanced my data problem. If I were to use the ratio strategy, again, as expected, I've kind of come all the way nearly up. I've come to 80% of the majority class. So good, some good options there. This next one is going to then do very similar, but is going to the undersampling. So again, I'm using the majority strategy now, and again, 80%. And this basically does exactly the same thing, except it's going to take records away from the majority class. So again, if I do this, you'll now see rather than having 500 in the majority class, I've now balanced it out at the 268 that was present in the minority class. So you can see how we can do those two things. Similarly, if I use the ratio strategy, you'll see that the majority class has now come down, not quite so much, but so much so that the 268 examples are now 80% of what is remaining of the majority class there. So again, just showing you some options that you can kind of tweak and play with when you're looking at these sampling strategies. And just for kind of completeness, this is sort of the over-under sampling there. So you can see that we've brought the majority class down a little bit. We've also raised the minority class a little bit. So potentially there is a good trade-off, a kind of best of both worlds approach there using that over-under sampling. Okay, and then we talked about stratified sampling. So if I look at the underlying distribution of the data as it currently is. So as I've kind of said, we've got 500 in the majority class and 268 positive examples in the minority class. That's roughly a 34% split. So roughly 34% of our data sits in that minority class. So we can actually do two types of sampling. So when we do a non-stratified sample, for example, we're not kind of dictating that the sample has to meet the underlying distribution of that target. So for example, here we've now up to 43% of the underlying data is now in our minority class essentially, but giving us our positive. Whereas if I use a stratified sample, you can see I've maintained my 35% split between positive and negative. So if we do want to sort of downsize the problem so we can just be a little bit more nimble with it, a little bit more agile, so it's a little bit more wieldy, we can use that stratified sample to make sure we maintain the same imbalance, but just with a smaller data set that we can then maybe do more with more quickly. I think the other one thing here was active learning. So for example, we can train a model. If we run some predictions through that model, we can have a look at the probabilities. So for example, this first row here, we can see it's right on the sort of decision boundary. It's not that sure about the probability there that it's kind of stuck this into prediction class 0. However, the other example here, it's very certain that this is a positive example. So these ones here were like, well, the model can very clearly separate that one. This one here, it's actually having a little bit more trouble. So for example, this would be a good candidate to maybe pass over to an expert who can correctly label this data if it was unlabeled and make sure we're kind of training the model through that. The last thing here is then classification metrics. So what I'm doing here is I'm going to just create a sort of a matrix that is all 0. So basically I'm saying if we had a model that just said make everything negative. I'm going to predict everything as negative and just see how I get on. We can see that the accuracy score here is 65%, which we know it was going to be, because we know that the 35% in the negative class has kind of been, sorry, in the positive class has kind of been removed now. So you can see here, if that data imbalance was more severe, and say 90% of our data was in the negative class, then this would come out with a 90% accuracy score here, which obviously is misleading straight off the bat if you're not aware of the problem of the accuracy paradox. But then just to kind of make this a little bit clearer, so we can also then use this classification report on an actual model that's actually been kind of properly fit and trained and all this kind of stuff, not optimized, I will say. But you can see we now get a bit more interesting information in our precision and recall metrics, and also our accuracy here as well. If we want to kind of zoom in on precision and recall, for example, or if we're using, for example, like an experiment tracking tool like MLflow, we want to pass in a specific, like a single value into a field in our experiment tracker, then you can also use this precision score function, recall score function, and F1 score function or F score function, which gets those values for you as just kind of scalar values that you can then pass into an experiment tracking platform, for example, like MLflow. So that's how you can use sort of a variety of different techniques to look at the different classification outputs. Right, back to the slides. So now we're going to look at some of the other approaches, and these ones are slightly more advanced approaches like SMOTE, or actually start to use the models themselves as opposed to tweaking the data to try and address the problem of class imbalance. So SMOTE, or as it's fully known as synthetic minority oversampling technique, is very similar to oversampling in the sense that it kind of adds data to your data set. It is upsampling your data. The difference here is that where oversampling doesn't give the model anything new to learn, SMOTE actually augments the data by finding synthetic data points or generating synthetic data points that the model can then learn from. So the way this works is essentially we identify a random selected data point in our feature space. So here we go, we identified one of those records there. We then pick 5 of its closest neighbors. 5 is a kind of a configurable parameter. So it could be 5, could be 10. You can kind of configure how many you want to look at. And then we pick one of those at random. So here we go, we've picked a random neighbor to that selected data point. What we then do is almost draw, essentially, in sort of inside the model, we sort of draw a line between those 2 data points. And what we can do is then plot on that line, anywhere on that line, a new data point, which we then know is going to have some sort of realistic relationship between those 2 data points. So that's kind of a good way of us giving a fairly good, well-estimated guess about what an additional data point might look like. And that's how we kind of arrive at this sort of synthetic augmented data set. And we can kind of do that iteratively over and over again until we have enough data points to sort of balance out our equation. Another way of looking at this is actually to almost reframe the problem. So we've kind of talked about this as a classification problem, but with unbalanced data. But almost you could say, well, is that not almost an anomaly detection kind of problem? And of course, in some cases it is. So there's a couple of ways that we can look at. There's many different algorithms that can be used for anomaly detection. I've kind of focused on 2 here, which are fairly easy to explain and to demonstrate. The first is isolation forests, and the second is a 1-class SVM. So I'll break those down for you a little bit now. So the first is an isolation forest, and this is essentially a decision tree based algorithm where the goal is to try and isolate as many individual data points as possible. And what we often find is then that the anomalies in that data will have the shortest path through your tree. And what I've got kind of set up here is on the left, I've got kind of the data set, and on the right, you'll kind of see what the tree would start to sort of look like. So what we do to begin with, we just kind of bifurcate the data, just chop the data up, as sort of with a random threshold pretty much through the data. So we kind of add that line in here, and as you can see, the tree then has obviously a logical split, 2 branches coming off in each direction. Okay, fine. We haven't actually isolated any data points at this point, so not so great so far. We then might make another split, and you can see we've been able to now isolate an anomalous, or what might be an anomalous data point there, using that second split. And we can then continue to kind of build up these splits here, splitting down our data, adding more and more nodes to our tree, until essentially we've either got to the configured max depth of the tree, or we've been able to isolate every single individual data point into a leaf node. And you can see that as the sort of anomalies come out, often they are the shortest path in that tree. So that's a good way of using the path length essentially to tell us whether something is likely to be an anomaly or not. And then obviously the forest element comes in, that we take these trees, we put them into kind of an ensemble called the forest, and then it's the kind of the voting of those different decision trees that gives us that indication of whether it's actually an anomaly or not. The other one that I mentioned was one-class SVMs. So a traditional binary SVM or a two-class SVM essentially uses a hyperplane to try and split the data as best it can. And it wants to kind of have that boundary as broad as possible, as big as possible. And then you see those support vectors that kind of meet the orange dotted lines. They're what tell it how far that boundary needs to be apart. That's kind of a traditional SVM that's using a hyperplane to kind of classify two sets of data. A one-class SVM does this slightly differently. So rather than drawing a hyperplane, it actually draws a hypersphere around the data. And what we can then see is that there are certain data points that sit outside of that hypersphere, and that's what we would call an outlier or an anomaly. So it's quite a simple kind of thing to understand, really. You know, we draw a ring around our data, whatever's outside of that ring kind of gets flagged as an anomaly. Obviously, there's slightly more maths and stuff behind that, but at the face level, that's kind of how that works. The last thing I'm going to talk about here is what's known as cost-sensitive models. And these can actually be very powerful in helping us to identify and solve a problem of class imbalance. And generally, the reason why we look at cost-sensitive models is that, typically speaking, a model doesn't penalize one type of error over another. So in this particular data set, we've got a few predictions. You can see the label in the prediction column, and we've got two rows here, DEF and GHI, where we've actually got a kind of an incorrect prediction. So in one case, the label was 0, but we predicted 1, so we thought they were positive. So we've that's a false positive, if you like. And we've got the other one where the label was 1, but we predicted 0. So there's someone that's kind of slipped the net, essentially. And obviously, in some cases, you might say, well, actually, that second error where this person was positive, but actually we predicted negative, our model misclassified that might be a much worse kind of outcome than the other way around. So therefore, we want to make sure that we're telling the model that you must reduce those kinds of errors as much as possible, even if it's at the expense of some of the other errors that you're going to make. As you can see there in that last column, the log loss of those two errors is the same. So the model can't tell which one is more important than the other. So what we can do is add class weights to these. So we can say, basically, if you make a misclassification on class 1, on the positive class, then we're going to amplify that by 10, for example. Whereas if you make a prediction that's wrong the other way, then that's fine. Just leave the kind of the log loss as it is. And you can immediately see now that the error that's associated to that particular misclassification is now much, much larger than if we'd left it alone. So using those kind of costs, those class weights, can really help impact how the model learns. So into the final demo now. Bring this across. So again, as before, I've loaded in my data using the same data set, and I've brought in some of the classes that I need. So the first thing we were going to look at was smote. So I'll print this all out properly again afterwards, but essentially we can define our smote strategy here. So it's giving our sampling strategy of 0.8, so 80%. And then we can actually put those, and I'll actually combine this with some undersampling as well, just to help balance it out. Put those into a pipeline, produce our data sets, and then if I run this again, you can see that before resampling, obviously we have our imbalance. After resampling, we've now got a nicely or slightly more nicely balanced out data set. Still a little bit of imbalance there, but then maybe that's not too much of a problem. And you can see here we've actually increased our class labels from 268 positive to 400. The one thing this doesn't really show, though, is actually whether it's generating synthetic data or not. How do we know it's not just replicating data? So what I've got here is, if I just run this piece of code, you can see here that this is the actual data that we get from the ground truth data, the source data. So we can say 135 women had been pregnant 1 time before, 103 had been pregnant twice before, etc., as we go through. But you can see they're all kind of pretty fixed static numbers. If I do this on the data set that's been applied, that's had smote applied to it, you can now see that it's actually generating some fairly spurious, someone's been pregnant 7.32 times, very spurious kind of results. But you can see that obviously it's, as kind of described, plotted data points, put a new data point in between that, and then generated some new examples that kind of fit within that feature space that are sort of somewhat realistic. So you can see that SMOTE has been applied here to be a more intelligent way of oversampling. Here we look at the one class SVM. It's really nice, this implementation, because it all sits within scikit-learn. So if you're already working with scikit-learn and SVMs, for example, then you can just make use of these SVMs straight out of the box, sorry. So you can simply do the standard sort of define your model, train that model and run a prediction. And then you can see here we've got our predicted labels in our confusion matrix, but also our kind of classification report as well, that we can use to identify whether this anomaly detection approach is maybe good or bad. Potentially it's not the best for us here. We're not doing any optimization on this, but maybe something to consider in future. Similarly for an isolation forest, slightly better on the old metrics, but again, would need some sort of refining. But you can see how, you know, it's not awful. It's a fairly good starting point and definitely something to consider when you're looking at an imbalanced learning problem. The last thing here then that we talked about is cost sensitive models. So here I've added this additional configuration of class weights, where I'm saying that for class 0, the weight you apply to the loss is going to be 1, so basically leave the same. However, for a class 1 errors, you're going to use a weight of 5. So you're going to times that by 5 essentially to kind of penalize that more. And by running that, we can see that, you know, we do have a slightly better recall and precision coming through from our confusion matrix there. We can also use the balanced configuration, which is almost kind of a best default, which I think when we run that through, yeah, it gives us some better metrics as well. So it's good to kind of start with the balanced. However, if you do a very sort of intimately close to your underlying distribution, then you can fine tune this using the class weights to kind of get that to be the optimum performance. Okay, and that's the end of those demos. So I think just to summarize, really, the key things I want to kind of hope people take away from this session is, number one, try and identify that imbalance really early. Ideally in that EDA kind of data analysis phase, identify what the kind of imbalance looks like and how that's going to trip you up with the various different nuances of your data science problem. Experiment with loads of different approaches. Don't be afraid to sort of shrink the data down if you need to try things a bit more efficiently. But use some of those simple approaches first and then try some more complicated approaches. Make sure you really validate the results you're getting after you've performed some sort of resampling or used a different model. Make sure you've got a good way of validating that is actually doing better than worse. Obviously, last of all, don't pollute your data set, your test and validation data sets with things like SMOTE or resampling. You want those to maintain the inherent imbalance so that you can ensure that your model can predict those and work around that imbalance.